Today we benefit from the expertise of two speakers who will be delivering this program together. First, Dr. Jingxin Wang is Professor and Associate Director for Research and the Director for Renewable Materials and Bioenergy Research Center in the Division of Forestry and Natural Resources at West Virginia University. He has taught forest and biomass harvesting and analysis, computing applications in forest and natural resources for both undergraduate and graduate students for more than 20 years, and has authored or co-authored 150 refereed papers and 12 books or book chapters. His research interests include biomass energy and bioproducts, forest carbon sequestration and optimization, computer simulation and system modeling, and forest ecosystem management and climate change. Currently, he is a leading PI for several USDA and DOE biomass energy and bioproducts projects. Jingxin's co-presenter today, Dr. Damon Hartley, is a computational energy analyst in the Bioenergy Technologies Department in the Idaho National Laboratory, where his focus is the modeling and simulation of logistics and pre-processing systems for biomass and bioenergy feedstocks. Prior to joining the INL, Damon received his PhD in forest resources from West Virginia University. He also has a master's in timber harvesting from the University of Idaho and a BS in wood science from West Virginia. Damon has also served as the Forest Industries and Timber Harvesting Extension Specialist for the Ohio State University and was a service forester with the Maryland DNR. Welcome to both of you. Thank you so much.
Okay, so can you guys hear me? Okay, thank you very much, Sarah, for the introduction. So it is my pleasure to present the biomass harvesting and logistics, especially modeling and optimization to the whole group. And also my pleasure to join together with Damon to do that today. And also Damon and I, we also welcome and thank you very much for all of you joining us today online. So if you have any questions while we are presenting, you can write something in the chat box. I think I have my assistant in here sitting with me. We can either write it down to you or either after presentation I can answer you back. So Damon and I, we have been working on this topic over the last several years and even before the new bio. So we are the co-leaders for the new bio harvesting, logistics, and pre-processing group. And over the last 4 or 5 years, and the group have been accomplished quite a bit things, especially the large-scale harvesting, storage, pre-processing, and even the techno-economic and life cycle analysis. So today we try to give you a quick summary what we have accomplished over the last 4 years regarding the new bio accomplishment from there. So before we start, I have, as I usually do, I have the quizzes, the questions, for all of you, and see how many of the questions you can answer at this point. But I do hope after the presentation you can answer all of them from there, So what is so-called biomass? Is a forest biomass carbon neutral? So why should we do the biomass energy, or either say biomass for bioproducts research and development? So what is so-called bioeconomy? Why should we do it nationwide and even see it for the whole world? We're doing this. So this is our presentation outline. So we try to give you overall review or overall view on biomass production potential in the country and in the country as well as in the Northeast. And we'll talk about biomass harvesting and logistics specifically, and talk about the biomass supply chain analysis and optimization, the method we're using, and give you some results and a quick summary from there, So this slide tries to show you how many tons of biomass this country can produce So as you may know, so DOE, Oak Ridge National Laboratory, so every 5 years they release a so-called billion-ton study report or update. The most recent update released last year in 2016. So the country, the whole nation can produce roughly 1.2 billion dry tons of biomass, with a potential biomass around 1.2 billion dry tons by 2040. And you can see biomass contributed roughly 5% of the energy need to the whole nation energy need, nearly 5% of the total U.S. energy consumption. It's about 4.8 quadrillion BTUs, and biomass is the single largest so-called renewable energy resources in the country, and has been increased, has been the so-called grown 60% between 2002 and 2015 from there. And the major biomass you can see pretty much produced from forest-based. And you can see I have a question in here. So what is so-called biomass and what is so-called forest biomass? So biomass primarily includes the agricultural and forestry resources, and also including the municipal solid wastes, and also algae, including algae. And forest biomass specifically include the whole tree biomass and forest thinning operations from forest thinning operations and forest residues and so on. And somebody may try to ask, so what is current say production level of our nation's biomass? So currently nationwide we can produce 709 million dry tons of biomass. So we are using roughly about 365 million dry tons of biomass for fuels, for engineering-based products, and so on. So this slide tries to show you the potential of biomass production in the Northeast. And you can see this map includes pretty much roughly 13 states in the Northeast. I didn't count how many exactly, but pretty much every state included in here. And that's one in here. So pretty much give you the stuff like the abandoned cropland area. So at county level in those states, and these area, for example, with a shining border, green shining border, so those counties pretty much part of the so-called BCAP programs. BCAP means a Biomass Crop Assistance Program funded by USDA, and you can see quite a few counties, also one county right here also, so in the Northeast. And also we provided so-called the residue production potential at the $60 per dry ton potential, and the dark color represent higher potential level from there. And also from the Dr. Larry Smart of Cornell, so that chart, that figure also show you the potential willow growth yield across the whole area, and even up to Houghton, Michigan, somewhere there, So pretty much like the willow yield could be up to 10 to 15 dry tons per hectare in a 3 to 4 year rotation. And reason the Kansas could be the annual yield could be from 10 to 40 dry tons per hectare. So according to our data so far in the whole Northeast, we can provide roughly 25.64 million dry tons per year of residue for, biomass in the format of residue. And for the price range from $60 per dry ton to $90 per dry ton. And considering the energy crops potential, so by 2030, the whole region in the Northeast, we can produce from 80 to 140 million dry tons of biomass in terms of short rotation woody crops and energy crosses by 2030 from there. So talk about the biomass harvesting and related logistics. So we understand in the whole Northeast, so traditionally we use a so-called fallow buncher. This fallow buncher, this is the machine in here. So fallow buncher, and we use a grapple scaler for the regular timber harvesting and pulpwood production. And when we talk about the biomass harvesting and logistics, so a lot of time we talk about the whole tree chipping, and this something also can happen in the not very common, not very often in the Northeast, but in the southeastern U.S., this is a very typical operation for the whole tree chipping operations. And in this area, the Northeast, for example, there's a picture by Mark S&D of SUNY ESF. So he gave it to me pretty much about 3 days ago, and that's the willow trials in New York, and you can see we use pretty much so-called forage harvester based from there. So what we try to say in here, for example, traditional timber harvesting machines equipment could not be optimized so in terms of production and cost for harvesting those energy crops, so such as let's say willow short rotation willow crops in here. So we have to think about how can we optimize this so-called willow crops harvesting, especially for example what kind of goal we try to achieve and what kind of potential challenges there we need to face each day. So the goal, as you can understand, for example, so for biomass harvesting in that picture in here, we try to deliver the certain amount of biomass to a certain number of facilities. So at the same time, we try to minimize the cost of delivery cost. So this is the goal for us for harvesting biomass. So the challenges for biomass harvesting we have. So typically, for example, compared to traditional timber harvesting, so the size on the crop size is way smaller, and also they are also spatially distributed, and the value of course lower, and their bulk density also lower as well. So those are potential challenges we have to face in terms of optimization of the harvesting costs and the logistics related costs from there. So move to the next one in here. So give you two pieces of equipment we are using in dealing with the biomass, for example. That picture in here, so it is a so-called John Deere 1490 wood energy harvester. So that machine can be used to promote so-called full tree utilization, reduce hazardous fuels, reduce logging site preparation costs, and can eliminate so-called in-wood chipping and provide long-term storage over chips. At the same time, can improve so-called transportation, logistics related handling of the biomass. So this machine entered the market in 2003, and because of the extremely higher cost, and this machine is not being so-called commonly used at this point, but it can create so-called 15 to 30 bundles of biomass per hour. And the standard bundle, like a log, could be up to 30 inches in diameter and up to 10 feet long, so weighs about 1,000 pounds. The bottom picture, for example, right here, it is a so-called dedicated harvester for short rotation woody crops. So that machine, of course, as some of you may already know, designed by Case New Holland with a Sony ESF. So this machine can handle the materials up to 6 inches, and the so-called one-pass cotton chipping and chip. The chip length could be up between the size between 0.4 to 1.8 inches. The productivity for that machine could be from 3 to 5 acres, harvesting 3 to 5 acres per hour. And I add a new picture, give you a close look at the harvester head right here. So we have the 2 circular saws. So once you're feeding the willows cut in here, at the same time, chipper behind those circular saws will chip the willow to chips from there. So that dedicated willow harvester, or we can use for harvesting poplar as well, hybrid poplar, and has been studied by Tim Wolf's group for the last several years already. And Damon and I were part of the team with Tim right now for the DOE project for so-called advanced logistics project at this moment. So since 2010, for example, the machine productivity has been increased dramatically. So in 2010, the machine can only produce, for example, 20 tons green tons per hour, and up to 2012, even now, could be up to 80 green tons per hour, the machine. But for machine operations in the field, we always try to optimize the machine's operation. We consider a lot for the downtime. So initially, the downtime of the machine could be was 70-something%, and now the machine, so the utilization rate is pretty high. The downtime is less than 10%. And if you look at this chart in here, and provided by Mark also to me, and they have done a lot of field trials and evaluate the productivity of this machine in the field, and summarize this chart in here. And you can see the yellow area in here and there. So there's also pink area, and also there's so-called green area in here. And that pink area pretty much means the productivity will be limited by crop and soil ground condition. And that part in here, so controlled or limited by so-called collection system, like this machine, the wagon in here with the harvester together, we call that system. And that one is primarily we call it collection system in here. And that part in here, the top part, yellow area, is limited by harvester itself. So the key things when we talk about the machine or system optimization, we primarily need to focus on this area in here. So achieve the highest so-called efficiency of the whole system, not the individual harvester and collection, but to combine these two machines with other trucks, also other machines together, we call the system. So this is the major area we should focus from there. So to the next one in here. So once we understand the whole operations, the ground conditions, the field-related characteristics, and we can go back to the office. We think about analysis and optimization of the whole system. So this is something, over the last 4 years for the New Bio group, we designed this so-called flow chart in here. So on the very top, we think about the supply chain configuration optimization. And beneath this, we have technical, economic, and life cycle. And our idea, we try to combine the whole thing together. Pretty much, so try to integrate technical, economic, and life cycle together right here. And we can provide results, not only dollar per ton, or even emissions, or emission something per ton. I'm sorry, so I have phone line calling in. So so the whole thing, for example, we can combine the emission and the cost together, give you say like say dollars per emission equivalent, like that. And using the same system design, the boundaries we got from supply chain. So this is something, it is our idea from there, And this is the whole chain. So for the whole Northeast New Bio group right now, and we consider, for example, those are the major feedstock components. We have 6 major components. We have feedstock, we have harvesting, we have the storage, transportation, pre-processing, conversion, and products, and so on. And the details components and each major part in here. And we primarily consider 3 major feedstocks in here. We have willow, we have miscanthus, we have switchgrass, and through all the process and reach to the final product. We have 3 major final products, including lignin, cellulosic sugar, and we have fuels, and we have the pellet, and so on. So, so this is something. We move to the next one and talk about the supply chain logistics and optimization model. So for the whole modeling process, as Sarah introduced us, for example, we have 2 major parts. So the first part is talk about site location optimization for any potential biorefinery facilities, and the second part pretty much related to the whole chain with consideration of site locations and so on. And the first part, for example, we use the so-called multiple criteria evaluation modeling. And the second part, pretty much, we use so-called mixed integer linear programming from there. And move to the next one. And we also consider the modeling process at 4 different levels. So from very top, so top level, the whole chain operations, and we consider logistics and conversion at level 2. And a little bit details at level 3, you see the major chain components from there. And level 4, we have very detailed processes. If you understand the whole process modeling, pretty much you understand what I'm talking about in here. So quite a few different detailed process in here, like say the operation for each component and the cost component and so on from there at level 4. So quite a few different methods, as I mentioned, that we used so far. And for the setting optimization, for example, we consider multiple criteria, and also we try to we integrated, for example, the so-called set suitability analysis together with the social evaluation criteria. So those are the primary factors. So including the feedstock availability, transportation infrastructure related factors, and terrain conditions, environmental related impact factors, and population, and even the social capital index also for the siting location optimization. So that's pretty much our study. Even we see the whole Northeast, but for that model so far, we consider these 3 major states in the Northeast: New York, Pennsylvania, and West Virginia in here. And we use so-called the social economic evaluation in here, and together with the fuzzy logic prediction model. So I can give you details if you need. Email me or talk to me for this modeling process. So that's pretty much the whole process for siting, location optimization, and you see the first box in here. So especially focusing on the site suitability analysis in here, So a lot of different factors in here, and transportation, feedstock, construction limitation, environmental impact, so on. So once you finish that part, we move to the next part in here. So we have the compromise programming and we need to rank these sites based on those site suitability indices in there. And then we move to the next phase, so-called social assets analysis. Pretty much we have creative capital and social capital. Those are two major categories in here. And eventually we combine those two parts together. We rank the sites and got the site's location and provide it to the users and the investors and so on from there, So that's something we have for site location, and we have to define what kind of values we use for those factors. So that's what I try to give you. So once you have the criteria, then we define the acceptable range for any potential criteria related to the site suitability index evaluation. So that's pretty much the fuzzy logic modeling model we used. And for the optimization part, for example, so those are the pretty much we try to cover in here. So what kind of supply chain component you consider? For example, these are components in here, feedstock, establishment, harvesting, storage, and so on. And what kind of process you have, as I showed you already on one of my slides before. And what is the model structure, and including say inputs, outputs. So we have there, So we consider pretty much the delivery cost from the site to the gate, biorefinery gate. So considering a lot of operational, economic, and environmental constraints from there, for the modeling process. And this is the logistic model structure we have, and so Damon is there. So Damon and I, we work on this for quite a few years, and at this point I have a couple other PhD students who are working with me on this modeling process there, So that model pretty much we have say 5 major cost components, and you can see the first one, it is a feedstock development related cost component. Then we have harvesting, we have transportation, we have processing, and we have storage, and so on. The objective, of course, is try to minimize the total delivery cost of the biomass from site, from the field to biorefinery gate. So this is the goal. Then we have to consider these constraints, restrictions, including availability of the biomass, biomass demand supply, and what kind of system you're using to handle these biomass resources, and storage system balancing and constraints. So in the modeling process, we pretty much considered roughly about 20 different restrictions or constraints from there, for this whole stuff. And so move to the next part. That means the whole integrated analysis and optimization. We also accomplished this part, so-called life cycle analysis modeling. And you understand, quite a few of you probably already understand what is so-called life cycle analysis. And we pretty much use a so-called ISO 14040 so-called standard series from there, So in this standard series, they mention, for example, 4 major steps to accomplish or to conduct this life cycle analysis. So the first step we always need to do to define the goal and the scope of our analysis. So our analysis pretty much from the cradle to gate, means from the biomass site to biorefinery gate. And we also need to define the functional unit, and we use 1,000 megajoules of energy or equivalent energy produced from the biomass for products. The second step, pretty much you need to define or identify or collect data to figure out your life cycle inventory, for example. So a lot of data you need, and the front end data site and the background data set, and so on. So for our new bioanalysis, we use a lot of field data from our collaborators within the new bio team, and from the feedstock group, and from the sustainability group, and so on. We have a lot of data from within the new bio. And for the data we cannot have from within the group, we have to use some other databases provided by, like Oregon National Laboratory, Idaho National Laboratory, and other existing data sets. And even the EcoInvent number 3 come with the CIMA Pro, so this is also used as a background data set for us. So the program, for example, the modeling process, tool we use is so-called CIMA Pro 8. That's pretty much the most current version we have. So step number 3, as I put in here, so-called impact assessment, and we can access 7 major indicators, impact indicators. So including fossil fuel energy use, and water consumption, and greenhouse gas emissions, and also a few other human health impact indicators. So those are stuff we evaluate. And the whole group, so we recently published a paper in BioFPR, biofuels, bioproducts, and biorefineries. So you can, if you want to know more information, you can download this paper or email me. I can send this paper to you if you'd like to know something about the LCA and TA analysis from there, And this table, of course, a little bit busy in here, but try to show you what kind of major parameters we have used in our model, and what kind of output parameters we can provide to potential users from there. And of course, they are all related to the 5 chain component, and we also have a so-called detailed model matrix used within the team. So this is something we can have details if you like to know more information. And this table tries to show you the major outputs and inputs from our supply chain and logistic model. And of course, for details, you can check with me. And you can see the major input, for example, so like feedstock development cost, establishment cost, feedstock yield, house equipment, machine production, and even processing facility and conversion efficiency, and so on. So quite a few input parameters. So the major output, for example, facility location, optimized housing system configuration, and delivery costs, dollar per dry ton, and by chain component, by process, and so on. And the final energy product, what kind of major products, the mix, and so on. Even procurement radius and distance, and so on. So those are major output from the model. And if you do analysis before, you pretty much understand we have to have the base case as usual. So the base case scenarios, and we define like this, and what kind of uncertainty or sensitive analysis you want to do based on the range, the change for those major parameters in the model. And these things, I don't want to read the number to you, but pretty much related to base case definition and uncertainty analysis. So results, give you some results quickly, and this is something based on our siting location model, optimization model. We have this stuff there. So suitable sites based on these major criteria, and these are the weights for those major parameters in here. And again, we use this modeling process already and got these results. The weight, and based on a lot of the checking evaluation in the region, so including the expert from academia, industry, and national laboratory, and so on. So we got this stuff, the results. And from there, for example, the site suitability analysis, we got the top 20 sites in those 3 states, and primarily you can see in Pennsylvania and New York. And out of these 20 sites, we further analyzed so 7 sites based on social. We select 7 sites after those 20 based on the further analysis from the social economic impact analysis there. The social economic analysis pretty much based on so-called creative capital score and the social capital values. I'd like to give you a little bit more explanation on these 2 terms in here. The creative capital score pretty much is used to evaluate the health, how healthy your regional economy is. So our value for those sites ranging from 0.3 to 1.6 compared to the national average value at 1. So means greater than 1, your site, your area, the economy health is better, and lower than 1, of course, a little bit poor. So this is why we can pick up 7 sites from these 3 states, and those 3, of course, with those sites with more than 1 CC, so-called the creative capital score more than 1 there, for these stuff. And the social capital values, we have 2 values there, the first one so-called non-rent seeking group score, and the other one CRR, census response rate. So that's a social capital value. Pretty much we use this to evaluate how willing and how accept so-called accept perceptive or acceptable the whole group or your community to the new industry, new biorefinery industry. So the point is, it means that if your economy is healthy and your group may not be willing to accept this kind of industry, and on the other hand, for example, some other group, they need the investment, they may be willing to accept the whole things. So that means, for example, with a higher value in social capital, so national average, for example, for this non-rating is 2.7. So anything above 3, and anything for this value CRR above 0.7, it means your community is willing to accept this kind of a new industry. So this is the results I can tell from there, So move to next one. In here, give you a little results in here. For example, so we have the logistic cost and by chain component and by process, by feedstock, by different biofuel products. But the key things I see, the costs vary according to a lot of different factors. But you can remember this. So the total biomass delivery cost pretty much ranging from $52 to $68 per dry ton. And the DOE targeted, for example, I think $60 sometime per dry ton. I think for some cases we have in the Northeast, I think we could be very competitive for that cost. And if you look at that table in here, for example, so I checked the most current the crude oil value at this point. For example, by March, the end of March, for example, the WTI Western Texas Index intermediate value crude oil price, it is $47.34 per barrel. And Brent crude oil, it is roughly $51 per barrel. So based on our analysis from biomass to oil to fuel, for example, our price still pretty high. You can see, so roughly about 3 times higher than the most current crude oil price at this moment. But this column and this for biopower generation, for pellet production, and if you check the price, I think they are very competitive and closer to the most current price we have at this moment. So, but the other thing, for example, you can see these lines. So for the same energy product, the price RSP means the required selling price using Willow could be cheaper, 5.5 to 5.8% cheaper. And producing the biofuels could be a little bit more expensive than the other two products. So those are things I try to indicate to you. And for the life cycle results in here, so that's only for Willow. We have the other two similar chart, spider chart for the miscanthus and also switchgrass. So as you can expect, for example, producing means biofuels. There's a red line in here, and consume more fossil energy and emit more greenhouse gases. And producing biopower means generating electricity, of course, consume more water than the other two processes. But we have detailed results for the other 7 indicators in here. So that's pretty much try to give you the how those factors, how sensitive those factors to to the required selling price, how they are related to each other. So we have the so-called internal rate of return, facility capacity, conversion rate, and transportation, and so on. And you can see how sensitive the required selling price to these different factors. So for sensitivity analysis. And move to next one, and this one also pretty basic. As I said, is also in the paper I mentioned to you. And let's give you the sensitivities of life cycle impacts to those factors as I mentioned, including the conversion rate, transportation distance, and the yield, and so on from there. And the next one is it is try to give you a quick summary in here. And we use process modeling and also consider so-called system balancing in harvesting operation. And these two things can more accurately describe and optimize the so-called biomass supply chain, which is very good way we're doing. And considering the social economic assets together with the site suitability analysis can further enhance the siting optimization in the rural areas. It's better. And we also see integration of facility siting decision and biomass logistics can better optimize the biomass supply chain and configurations from there. And next slide, also quick summary. So successful development of this industry, so biorefinery, biopower industry, will depend on efficient logistics. So this is the key. So delivery cost of biomass varies according to a lot of different factors in the chain. So harvesting, transportation are the major cost component. Integrated TEA, techno-economic analysis, and LCA, life cycle analysis, could be a good tool for future biomass supply chain analysis. So we have to consider the value-added product from biomass. Otherwise, it could not be compete with the fuels, the fossil fuels at this moment. And we have to think about integrated production of bioenergy and bioproduct together to improve the whole so-called economics of the entire supply chain. And before I finish my last slide in here, my information, thank you very much everyone for joining us. But I believe, Damon, you can add something related to the results if you like, anything, citing models and supply chains. Anything, Damon?
Can everybody hear me?
Yes.
Okay. Well, my mic my speakers kind of cut off, so. I think just what you were summarizing at the end is kind of the important takeaway that, it's an integrated type analysis is what is going to drive this going forward. So that's what we should be striving towards. But I'll be more than happy to help answer any questions if there are some.
Okay. So we still have about 12 minutes. I mean, if any of you have any questions, so we try our best to address or answer you.
Yeah, please type them into the chat pod. Oh, we have a question already from David. He writes, it seems like there's a need for an entirely new industrial sector to make the harvesting machinery for SRWCs. Harvester material capacities increased 3 to 4 times from 2010 to 12. Are we close to having equipment that is financially worthwhile to make? What is the projected payback time, and what is the harvest required to break even? How does this compare to switchgrass harvesting efficiencies? So before you answer this, I'll mention, David, that we have a few webinars that focus specifically on willow harvest equipment and logistics in our archived resources, so that might be something you might want to look at. Damon and Jingxin, how do you compare availability and efficiencies of what we have here versus, for example, a more developed set of available equipment in Europe, for example?
Okay. So, Damon, would you like to start?
Sure. Yeah, that's just kind of what Sarah was saying is, the equipment's out there, and they've been doing this in Europe for a while. But, adapting to slightly different forms of material and different land-based requirements, we have a little bit of room to grow. But I think we have a good base in which we're starting, and looking at the new Holland machine is definitely a step in the right direction. And as far as so I think I think the analysis shows that equipment is worthwhile and is making economic sense. It's more of a case now of having areas that have enough to keep machinery utilized. The equipment works just fine. It's having producers produce the material. That's the other half of the economic equation that we have to deal with.
So David, it is a good question, David. I appreciate it, huh? So, as we all know, so this biomass harvesting has been very developed machines, internal machines in European countries. Like I was in Italy last November for a whole month sabbatical leave, so they have equipment for popular harvesting. It's very developed. And talk to you regarding, the payback. So it depends. So I'm thinking, the new, if you have, for example, the new case New Holland, pretty much they have two separate pieces. The base machine, the forage harvester. So the farmers, if they already have this, it is good. They have a new one. This payback period could be longer. But for this harvester head, the carcass hider, as I know, it only costs about $30,000 to $40,000, and that's payback. For example, if a farmer already owns a forage harvester, they can only need to buy this carcass hider. So that payback period, in terms of harvesting costs, whatever, could be shorter. Like say within 5 or even say 8 years, or even shorter, huh? So that could be this, but we don't have this kind of analysis at this moment in terms of say purchase the machine itself or purchase the hider itself or combined. But we can do that and talk to you. Give you the information at a later time. But I think it could be very good for the payback time period. And harvesting, for example, talk about break-even harvesting in terms of cost per hour and dollar per hour. So that's also another good question at this moment. And I do believe, as we talk, for example, so the range I have, so 50 to 60 something dollars. So that's pretty much, within the break-even range for the cost. It means beyond, higher than that, of course, the benefits for harvesting could be higher. But lower than that, if you reduce the cost from there, and that will not be beneficial to the potential machine operators at all from there. So for the cost of break even, and compared to the switchgrass harvesting efficiency, I'm thinking so the efficiency for switch and any grass harvesting, it is also pretty much mature, also developed. And this efficiency we are still improving, and we are getting there and getting closer to it. So at this moment.
Specialty harvest equipment is also likely to be something that's contracted out and not necessarily something that every single producer would purchase and own him or herself. So regional density of acreage is something to consider as well there.
Yeah, that is also a good point, Sarah. I think a lot of say independent harvesting contractors, they can do that. So for example, that person purchased the machine and contract the machine out, and even the operator out to do the field work for the other landowners and growers, and that could be reduce the cost to some level. So which I do agree.
Well, and I think that's kind of what the thought is you take groups are already contract harvesters, and because the harvest generally happens over winter, this is something that they could add to their services option, which would, they already have the equipment and they move through.
So I saw Veronica and Charles also ask questions, and Veronica especially asked us, say, how did you decide on which social and environmental factors to include in your analysis? And this is also a good question for Veronica. Thank you. And pretty much we have done this quite a few years, and a lot of the references out there also. And the environmental concern, for example, we primarily focus on something related to site potential site damage and potential water issues related. And for social, for example, social factors, we pretty much try to consider the social acceptance, regional economic health, and population related, and those kind of things. So pretty much, as I mentioned, we follow pretty much the nationwide. We don't say standards, but we say the procedures nationwide we use. The social capital related. So that's is pretty much accepted, or either say being used means for a lot of potential modelers for those kind of analysis. So anything you want to add, Damon?
Yeah, just the environmental factors were garnered from kind of a synthesis of citing studies done in other industries and looking at what the commonalities were and knowing what potential environmental issues there would be with a biorefinery.
Yeah. So Charles, for your question, I think the answer is yes. Definitely we can adapt the model to a Michigan area. There's no question about it. So only things that we need to change some kind of conditions related to even social economic related, or so-called feedstock availability, demand, supply, and even we can use the feedstock yield in your region. I don't see any issues. We can use the model in Michigan.
All right, we do have time for a couple more questions. In the meantime, please type those in the chat pod, but in the meantime, let me pitch a few of my own. So to be clear, a point of clarification here. The modeled cropland projections that you showed at the beginning are combined, in your case, with timber harvest residues for this spatial analysis. Some models consider only one or the other, but especially when you consider short rotation willow with timber harvest residues, it's likely that a facility, even if it's not decidedly feedstock agnostic, might be able to use both of those things. And certainly a more realistic market view considers both in procurement. So in the process of this modeling, did you learn anything about whether a given facility would be more or less likely to depend on one or the other feedstock type based on factors that go beyond just geography, or whether some combination of both in a procurement scheme is optimal based on certain sets of conditions, or is that a bit beyond the scope of what you did?
Yeah,
no,
I think. Go ahead, Damon.
That's kind of exactly what I did during my dissertation. So, and really what we found is it's a temporal mixing of material. There's definitely a preference for the short rotation when it's available, but then you can't, because of some of the quality issues. But then as you move into the timing where short rotation might not be as available, it will definitely just pick up with the forest material, and it was kind of unanimous across the regions that would happen.
Gotcha. So time is the really big factor when it comes to hedging and risk mitigation in that sense. Okay. Here's one more question I have for you. For those of us who aren't familiar with what it's like to work with these really large data sets over large geographic areas and integrate these models together, certainly a really key advantage of what you've done and what makes it so fascinating and important is the fact that you've integrated these models together. But are there risks associated with integrating models together? Can you, for example, compound some of the uncertainty within each of those models that you're pulling together, for example?
I think that's definitely the case, and you have to be very careful that you're designing your models to be combined, and taking disparate models and trying to combine them won't definitely, but is more than likely going to cause you issues down the road.
Mm-hmm. Yeah, I think yes. So pretty much it means integration models always have some kind of potential risks there, because different model, by different group, they pretty much initially, develop model initially based on different conditions. So by doing integration, we have to be very, very careful and checking the conditions and adjust all or any potential parameters. That's why for modeling, the base case definition, design, and even the uncertainty things there are very, very essential. So, and we have to, if we try to present the results or try to talk to the other general groups, for example, the modeling, they always question us. How do you adjust these? How do you change these? For the modeling integration. So, which is, we will involve a lot of different factors, of course. So at that moment, for example, so Damon and I, and even the Oak Ridge National Laboratory, so the three groups, we try to integrate the Idaho National Laboratory so-called biomass logistics model, and with WVU logistics siting and optimization model, with Oak Ridge National Laboratory so-called IPCEL model. So those three models together try to work together on something, and we have been talking quite a few times already, and we already pretty much clear how to say integrate the thing together, and through the parameter adjustment, base case definition, uncertainty, integration, and so on. So which is good there. I think we're getting there also for the model integration. And I saw Dave will have another question there, huh?
Yeah, so David's question asks about the life cycle analysis, specifically greenhouse gas emissions. So he talks a little bit about, the variability between pellets, biofuels, etc. He asks about how these results compare in your modeling experience to coal's emissions profile. How robust do you consider these results to be in supporting the claim of improved greenhouse gas emissions? So I might add on top of David's question, we've seen in the last 2 weeks policies to quote reflect carbon neutrality of forest biomass. So I know this isn't a policy talk, but you obviously mentioned this as a foundational question at the beginning of your talk. So I guess just curious to hear your thoughts there.
So yes, so back to Dave's point. The baseline, for example. So we also did another project for USDOE, National Technological and National Energy Technology Lab in Pittsburgh mountain area. So we pretty much try to use coal emission same amount of energy or produced with compared to biomass as a baseline. How Dave? Then we compare to if we use biomass, or we either say we mix certain percent of biomass with coal, how those things can reduce the emission. So under the condition of biomass is some kind of biomass neutral. This is my question, because a lot of people argue so biomass is not carbon neutral, but to me, I have a paper, not published yet, but one of my students put together already. So we have a curve, so the biomass neutrality curve. So it could be ranging from 0.5 to 1 or even over 1. So we don't consider even say 100% biomass carbon neutral, but it should be some level. This is my argument. So that's why we have to consider biomass carbon neutral to some point, and we compare it to the coal as a baseline, then consider the greenhouse gas emission from there. So this is something we did for this.
Okay, thanks. So we're running right up against the end of our time here. If there are any last minute questions, feel free to type them in. But in the meantime, I'll just ask Jingxin and Damon, do you have any final thoughts you want to leave us with before we head back into our work in the bioeconomy today?
Yeah, I'm thinking so. Even we have a new administration, and I do believe biomass for bioproduct, for biofuel, for value-added products should be some kind of future. We should continue to work on this, and this is renewable and can also help the rural economies in the country. So those are two key things. The USDA and DOE has been promoting all the time.
Thanks. Damon, anyone want to add?
Oh, yeah. I said I'll just kind of second that, and say that it's going to take an energy mix to solve our energy crisis here. So we can't. I don't think it's reasonable to exclude any technology.
Great point. Thanks for that reminder as always. Thank you all for joining us in this program today. We hope to see you on future webinars. Have a great rest of your day.
Thank you, Sarah. Thank you, everyone.